at least to start off with, is trying to get rid of that thing in the corner, but we'll live with it, I suppose. Okay, so propositions as types, right? So how many of you have heard of this slogan, propositions as types? Excellent. Okay. For those of you who haven't, I've got enough. So we're going to be okay. So that's the rest of the first bit of the talk is for you. So this is kind of following what Philip Wadler has done, who was just mentioned just recently. So I also want to add to, so I'm going to, as Arnav said, I'm going to give you a glimpse of what goes on, and the kind of things people are thinking about, especially me, what I'm thinking about. And more importantly, I do want to point out that theory isn't hard, it just looks hard, at least in my kind of experience, right? Okay. So the starting bit of this is, I think TypeSig, we're hoping to get Bob to speak, Bob Hopper in programming languages, like a pioneer in programming languages, to give a talk here, right? So the thing you need to know about Bob is Bob Hopper is an authority in programming languages, who's done a lot of great work, right? Lots of interesting work. The thing about me is, well, I've been reading this book called Authority and the Individual this week. And the thing that's been on my mind this week is, what are authority and the individual, these two ideas, are they in contrast with each other? Are they, towards social cohesion? What do they mean, right? So I started reading this book because I realized I had a problem with authority in general, like centralized authority and political authority, that kind of authority, right? So this is why I'm reading the book. But if you take these two things into context, do I hate Bob? That doesn't make sense. If I hate authority and Bob's an authority, do I hate Bob? But that's weird, because that's not really my point here, right? Because there's two different meanings in which we're looking at. The first thing, when I say Bob is an authority, I mean Bob is an expert in programming languages. And the second thing, when I'm saying I hate authority, I'm talking about something completely different, right? But the problem here is that we're looking at the same set of, it's the exact same word that we're looking at, it's the same symbol, except it has different meanings. And the context is completely invisible when you write it down, unless I write down more, right? By the way, I don't, just so we're clear. Don't want to get canceled from PL. Yeah, okay. So what we need, or what we would like, right? Of course, English is great to kind of communicate, write poetry and that kind of thing. But what we would, to reason with, to think about logic, we would like an unambiguous language with unambiguous symbols. That brings us to kind of a formal logic, right? Where most importantly, where a symbol has a fixed meaning. So for example, if you have a symbol P, now P means true and it doesn't change. It's either true or false, for instance, right? But it's a fixed meaning, and this is the most important feature, one of the most important features of formal logic, right? So let's talk about what is this formal logic. So we're going to look at intuitionistic propositional logic, or just propositional logic to start with. The language of propositional logic has a few symbols. It has P, Q, R, and so on, and then it has connectives where you can say if you have A and if you've got B, then you can say A and B, and A implies B, and so on, right? There's a number of connectives which you may have come across already. And it's this is basically, you can think of them as atoms in the formal logic. So these allow you to give you a little bit of vocabulary. But how do you write sentences and kind of write stuff down in this logic is what we're going to do is what we're looking at here is, if you want to show, or if you want to prove A implies B, you start by assuming A and then you prove B, and then you can infer that A implies B, right? This is just kind of a natural thought process that we're writing down as formal rules in logic. On the other hand, if you've proved A implies B, by prove I mean you've just written down a few things and you've inferred A implies B, and if you also know that A holds, then you know B holds, right? This is the implication elimination, right? So now this is how you kind of construct a formal logic, and also now there's a few rules about conjunction. If you have a proof of A, proof of B, then you know A and B holds, and we typically annotate so we know which rules we're talking about. We're going to annotate each rule with like a little note saying this is a conjunction introduction, right? Because there are other kinds of rules, because elimination rules. Elimination simply in the sense that this symbol disappears. This should be a conjunction instead of a times. And yeah, so there are two elimination rules. If you have an A and B, you can either infer A or B, right? Depending on what you're looking at. So here's a little proof also from Phil's paper. It says if you assuming B and A, we're going to show B and A, and assuming B and A, we're going to show A and B, right? So the way in this system that we've set up, in this formal logic that we've set up, what we're going to do is we're going to start by assuming B and A. If we have B and A, then we have A. We also have B. But if you have A and B, then you've got A and B. And then now you know that you have B and A implies A and B because B and A was an assumption to start with, right? And to point out what's going on here is that every assumption here, the assumption's used more than once. So I have to mark that it's the same assumption. So I mark it with a little z here. And the moment that I know I'm done with the assumption, I don't need anymore. So I'm going to close this with an implication introduction rule. And then I kind of get to infer that B and A implies A and B. So I may want to do something else instead, right? So in the same logic, because we're just kind of writing about reasoning, we may want to write B and A. We may want to do the same proof as before, but in the end, instead what I'm going to do is I'm just going to eliminate, apply an elimination rule, because if I have A and B, we know that we can infer B, right? But this is a bit of a silly thing to do because I started off with B and A, did all of this stuff, and then I came down to arrive at B. We could have just started off with B and A and said, well, if you have B and A, you have B, right? So this is a much simpler proof than the one before, right? So the thing that I'm pointing out here, there are many ways to write proof of the same formula, right? If you want to prove the same formula. So there's a notion of a more complex proof and a simpler proof, and you can take a complex proof and reduce it to a simpler proof. So this is the notion of a proof simplification, right? So that is the context for what propositions in the propositions as type slogans mean, right? Propositions from propositional logic. On the other hand, now we're going to talk about types. So types come from well, more than what they come from. We're going to talk about types in the so-called type lambda calculus. And types also look a lot like propositions, possibly with different symbols. In this case, what I have, types should be somewhat familiar to us if we're programmers in computer science, right? So we've often, depending on which language you're looking at, we've got function types, we've got a product type, and then we've got like a base type, right? Like int, bool, and so on. If you don't have these types in your language, it's time to change, I think. Yeah. So right. So with these types, now there's a question of what kind of programs can we write? Right. So now these are again ways. So if we had a language, we would start by writing down what kind of programs can you write in this language, right? We would write down a syntax for it. So that's what I'm doing. But in addition to the syntax, I'm also going to write down the so-called types alongside them. So this basically says this term T has the type B in some context. Context is basically the way of saying we have things in scope and what can we use in the term, right? So this term is basically saying that if you've got a term of type B which started with A in scope, then you can abstract over it, meaning lambda is a way of abstracting over variables in the context, and you have that lambda z dot t is of the type A to B, right? And now if you have a function and then if you have an argument, you can apply them together, and then you have a term of type B, right? So these are the most basic primitives in the lambda calculus. So you also have products, right? So products being times here. So products are pairs sometimes. So you have a way of constructing pairs. So if you have two terms, T of type A, U of type B, then you can kind of pair them up, and you can also eliminate things from a pair type, right? And the kind of programs you can write in this, so you don't worry about types so much when you're writing about this, because you just write the program, right? Because when we're writing things, even in functional programming language, you don't see all this gamma, A times B. Well, you might see A times B, but you never see gamma, right? Because it's kind of in the scope of your things, which is what we refer to as scope in programming languages. We just kind of go ahead and write the program, and that's what we're going to do here. So this program, what it does is it takes a pair. We don't know it's a pair, but I'm telling you it's a pair because we're going to find out it's a pair. It takes a pair and then computes a new pair where it kind of swaps the argument, right? So because it constructs a pair where it takes the second component, puts it in the first, and takes the first component, puts it in the second place. So you've got this new kind of swapping program. Right. So now, so why is this a reasonable program to write? Why is this not complete nonsense? It's because we can assign types to it. So types kind of make sure that this program, when you write it, is actually a sensible thing to write, and we've not applied the wrong operations to things of the wrong type. So for example, it wouldn't make a lot of sense to add 1 to hello. I mean, unless you're writing Python or something, but in a primitive sense, right? A string and an integer are different things, right? So in that sense, right. So here, what's going on is basically this is just spelling out what the typing rule of this particular term is, even though this is what we were interested in. It basically says if the given thing, that is the z, is of product type B times A, then you can take the second component of it and you get the A out, and you can take the first component of it, get the B out, and then you construct a pair with them, and abstract over them. So in the end, you get a function from b times a to a times p, right? Once again, you also obviously have a notion of program evaluation because we write programs, so we can run them, right? So if you had a program which said something like lambda z, where you project out the second component of a pair that you just constructed, you might as well have not constructed the pair, right? So you can just get rid of this operation, and instead you could have just returned the first component of the pair that you were given in the first place, right? So this is the way of simplifying programs, but this is exactly the concept which is applied for evaluating programs. So we've morally done something which looks quite similar to each other, right? On the hand of formal logic, but we're completely different considerations where we're just talking about reasoning and about truth and that kind of thing. And on the other hand, we're talking about taking values, kind of breaking them down and doing things to them. The key observation of propositions types, or sometimes called the Curry-Howard correspondence, is that these two things, the terms that you write, the proof terms that you write, and the program terms that you write have the same structure, right? This is kind of the key correspondence. But when you throw this, when you just look at this particular slide, it's hard to tell exactly why this is the case, right? So, but when you zoom in, it becomes a little bit more clear. So now when you look at this particular kind of proof term, subterm in the proof, or sub-proof, if you will. So here it basically says if I've got B and A, then I can infer A. But you're doing a very similar thing when you're writing a program. If you've got a pair of B and A, then you're projecting out the second component, then you've got a thing of type A, right? And if you look at subparts of this proof again, once again, when we were reasoning about implication introduction, we were also we were writing a corresponding term about lambda abstraction, right? Using lambda abstraction. So once this pattern kind of starts to show itself up, you go, oh, okay, so these are exactly the same thing, but we're just using different symbols, right? Which kind of gives rise to the speculation first about, okay, maybe propositions have something to do with types. And then now when we go back and look at these languages, the languages being the specification of the propositions as types. So right now, the way I presented, this looks like these are the same thing, but historically they weren't, right? They were considered in completely different contexts. One is credited to Gensen, the natural deduction one, and simply type lambda calculus is due to Alonzo Church, which has happened around 1940, I think, while natural deduction somewhere in the 1930s. So the first observation here is that propositions and types look similar, but they are the same. Here, all I have to do to bridge up this difference between the atoms and the base type is basically just, this is just a syntactic difference. You could just say that we have one base type for every propositional atom. But apart from that, it's quite intuitively, it's easy to see that conjunction and times are roughly the same thing, and implication and the function type are the same thing in the sense of as. Right? So that leads to the first kind of observation that propositions as types, even if we ignore programs and proofs and all that, propositions as types in the sense that these two things are the same, you can map back and forth, right? But of course, if that was it, that would be a very uninteresting correspondence, though. So it goes deeper, of course, where you can look at proofs, right? And you can say, well, that corresponds to programs as well, just what we were doing. So you can say the implication introduction is the same as the lambda abstraction, and that leads to the next step as proofs as programs. And you can also go all the way to saying that simplification of proofs, which has completely different considerations, is the same as evaluation of programs, right? So all that is well and good. Is propositions as types useful? I mean, it takes work to study this thing, so it's worth asking, why are we doing this? I mean, it's really cool. I think it's really cool because it's amazing that two kind of fields of study kind of overlap with each other. But is it useful? Should we keep looking at this, right? But from what we've understood so far, from what we know so far, even if we stop studying it now, we've got a lot to take away, right? We've got all these proof assistants. We've got Rock, formerly known as Coq, and then we've got Lean, and then we've got Agda. And of course, these theorem provers are great because now you can kind of you get this feedback with the computer, right? You're writing a proof, and you're not just doing it on paper. The computer tells you you're doing it wrong or you're doing it right. It gives you a little bit of feedback when you're doing the proof, which is amazing because now you have this theorem proving for hackers, right? Even if you have no background in formal logic, you can just fire up this program and you can start playing around with it. And it tells you you don't need to study formal logic for a long time to actually start and do proofs in formal logic. You can just kind of play around with it as if it were a programming language. So this is an important innovation. This is in my opinion. So the next question is, of course, is propositions as types a coincidence? Is it just a one-time thing? Should we keep looking for it? First of all, second of all, moving on. Right. So modal operators. So I did say something about going to talk about modal propositions as types. So what is this modal thing, right? So right. So again, now going back to logic, just considerations of the relationship about reasoning, about thoughts, or just philosophy, even, if you will, right? And we want to talk about certain patterns of reasoning, and we want to bring them down to a logic, right? So one pattern which comes up is, for example, when you start thinking about thinking about authority, individualism, that kind of thing, you could start speculating whether authority necessarily threatens individuality. And necessarily here is kind of strengthening the original statement, right? It's saying this kind of provides an emphasis, saying I necessarily think this is the case, right? So, but you could also go the other way. You could say, maybe no, maybe that's too strong of a statement. We don't really know what we're talking about properly. So maybe we should say something safer, like possibly. I'm not really sure. And possibly is kind of going in the opposite direction. It's not strengthening it. It's kind of diluting the statement. You're saying, well, possibly in some cases this might be true, right? So which leads naturally quite to the notion of modalities, where we say something is necessarily true or something is possibly true, and we denote them using, because it's cumbersome to write this every time, we're going to just throw in a box and we're going to call it necessarily, and we throw in a diamond and we're going to get possibly, yeah. So, and of course, and previously when we started off with the logic, we were going to start off with proof rules. But even before we start thinking about how do we reason in this logic, in the sense of how do we write proofs in this logic, first you have to say, what do these operators mean to you, right? Because these are necessarily and possibly, these are kind of vague notions. So we have to be a bit more specific as to what exactly we want out of these modalities, right? So what the question which comes up, or which has come up, is basically it depends on your application. So for example, in computer science, you might have heard of something called temporal logic, right? In philosophy, you have something called epistemic logic. And all of these are modal logics, except they have different concerns. What this goes to say is that you don't always want certain formulas to be true in your logic. So for example, you may have a logic where box A implies A. If something is necessarily true, then it's true is a reasonable thing in many cases, but not all. And if A is true, for example, then to infer immediately that A is possibly true is a safe thing to do. Most of the time, right? So, but not always. So it really, the first question which comes up is what kind of formulas do you want true in your logic? Which also says there's not one modal logic, there are many modal logics, right? So it's a broad term when we're talking about, unlike proposition logic, which is one logic, here we have a whole range of logics depending on what your applications are, and there are many which are documented, right? So this is the logic side of things. On a completely different world, right? So modal logic already started in the beginning of the 20th century. And towards the end of 20th century, Haskell got its first functor type class, like Haskell at the time being a baby programming language. And it gets this type class, which says type class being an interface, as the closest approximation being an interface. And it says fmap, and the fmap is the name of the function, which says if you have a function from A to B, and if you have f of A, then you can get an f of B. And f here, one instance in which you can think of these f's as kind of a container of A, right? Or you can think of it as a collection of A even. So for example, one example of f is list, right? So if you have a function from A to B, and if you have a list of A's, you can kind of apply this function throughout the list, and you can get a list of B's, right? So this is the notion of functors come up in Haskell and programming languages in general, but it shows up in Haskell as a real language that we can kind of look at. And you have further refinements of it, right? So functor is just an interface. As in Java, for example, you would have special interfaces which specialize the base interface. So here you have something known as monads, and monads are basically an extension of functors, if you will. They have two more operations. So they have something called return and join. And return basically says if you have value of type A, then it'll give you a value of type MA. And join says if you have M of A, then I give you M of A. Similarly, you have the opposite, comonad, where you just kind of flip everything around. Instead of saying A implies MA, A to MA, you say WA to A, right? And I think this W is just because yeah. So it's just because if you write it upside down, it becomes the M. I didn't because I was looking at the Haskell spec and I was like, why is it W? But eventually it hit me. So right, so these are different kind of interfaces that you find in Haskell. And so now, but we have an awfully similar looking thing. We've got these so-called co-monadic types and monadic types. And these look a lot like modalities. And if you line them up, right? If you line up the axioms that I was talking about, axioms being the formulas, the formulas that I had written up earlier, and said these are the things that you might care about. And if you look at what a comonad is and what a monad is, these things look awfully similar, right? So it's very reasonable to start speculating whether these are the same thing in the sense of as, right? Like propositions as types. So is necessity, can you think of it as monadic type? Can you think of possibility as a monadic type, necessity being a co-monadic type, right? It's a very reasonable speculation. And this already started in 97 here. So we've got a lot of work has been done on this, right? We've got propositional X logic, which started off in 97, says, oh, here's a logic for monads. And it doesn't say logic for monads. It says here's a logic which looks a lot like monads. So to be fair, and this then there was another logic which said, okay, we know monads. Can we do a a logical reconstruction and come up with the logic, right? Because we don't. At the time, at least, it wasn't clear what the logic of monads were. And then there's a judgmental reconstruction of modal logic in another paper which is talking about comonadic types. All right. Point here being there's a lot of work trying to bridge this answer this particular question. Right, but this was all written in the right. So the last one of this being in 2001, right? So then, of course, this work went on. But in spite of a lot of interest in this area, if you look at Philip Wadler's 2015 paper on propositions as types, and let's read the statement. It says, some claim that each of these variants has an interpretation, each of these variants being each of these modal modal work on modal logics has a form of computation via propositions as types. And a down payment on this claim is given by an interpretation of S4 as stage computation due to Davies and Fenning, right? So Davies and Fenning being these two sets of works. So the thing that I want to point out in this phrase is the rest of the paper is all like authoritative, right? It says propositions are types, proofs are programs, and it really is a strong statement. It really shows you evidence for that. But here things start to get a little bit like some claim. There is a down payment, and if you keep reading, it'll say Benton, Bierman, and DePaiva observed that monads correspond to yet another modal logic differing from all of S1 and S5. So the thing over here that we should really be kind of taking away is that there is some hesitation in accepting this, which I think is justified, and also there's a little bit of frustration, right? This is my interpretation of these sentences. You can go ask Philip Wadler himself. And there's yet another modal logic. So clearly, this doesn't seem to be a consensus in 2015, which is well after the kind of works that I showed you, right? And this is because there are a number of conundrums in trying to bridge these things together. So one example of this is monads, for example, are monads are a functor, which means they have this operation which says if A implies B. Sorry, if you have a function from A to B and then you have a monadic value of type MA, then you can get a thing of type MB. This is a strange, so now I did say the monads M corresponds to diamond. Now this is a kind in modal logic, this does not have any, this stuff is not found in modal logic literature, right? So it's kind of a strange axiom to even to write down, because it's like, why would you do that? Because it's not clear from a logic standpoint why you would want that. On the other hand, if you look at diamonds, the possibility modality, it has this property which says that if A or B is possibly true, then possibly A is true or possibly B is true, which is a very reasonable thing to say, but this does not hold for all monads, right? So this kind of doesn't break, but really brings the question about the relationship between monads and possibility, right? Or more generally, modalities and these kind of funky modal functor operators that we're looking at. So which brings me to now about modal propositions types. So let's think about what really is going on here. So if we look at our original understanding of propositions as types, it basically said propositions as types, proofs as programs, and reduction, simplification of proofs as simplification of programs. It should have said constructive proofs, because we're really talking about proofs and their construction, right? If you looked, we didn't just say proofs in the sense of like abstract proofs, they were actually being constructed, right? So it really should have said constructive proofs. So I've just kind of filled that in here. So the problem in the modal logic case is this bit, right? You no longer have, it's unclear, because first of all, there's a number of modal logics, so you can't just take this one proof system and say, oh, look at this, the syntax of this thing, look at proofs in this thing, how does this correspond to the things in a language? We can't do that because we don't have this one thing, right? So now if you go around asking for a proof system for modal logic, the first question, the counter question you will get is which modal logic, right? Because of many modal logic, and quickly you will realize there are actually more modal logics than proof systems for them, right? So this is kind of the crux of the issue where we like this propositions as types correspondence, but we can't make progress because it talks about programs and proofs, but we don't have proofs because we don't even have a proof system. So now here we are, right? Now what am I going to put here? Because to fill this, to kind of close this gap. So which brings us back to the question, the dreaded one: is propositions as types a coincidence? I hope not, but and this is how you would. We hope not, because this seems to be useful. But propositions as types, the first observation that we need to make is propositions and types are meaningless in the sense of intrinsically meaningless, right? They're just symbols, right? P doesn't mean anything. It's just P. You have to say what P means. You have to say P is true, right? So what we've been doing so far is we've been saying, look, A and B, look, A times P, aha, same. But really what we meant, or what we could benefit from in the cases where we can't do the same, is we actually look at how things are interpreted and see what we mean by these things. And then that would give us a little bit more opportunities to understand things a bit more, because sometimes you don't have the syntactic representation of your logic. So what we're going to do, or what the proposal of the kind of work that I'd like to do, I am doing, is not look at propositions and types by themselves, but look at the meaning of these things, right? Look at the meaning of propositions and look at the meaning of types. So on this side, what we're basically saying is look at the so-called denotational semantics, or like semantics of programs, right? So mathematical semantics, if you will. This is in programming language, we're quite used to. We study this as we study programming languages as well. So we've got semantics of programming languages. So I'm going to focus on this bit. So if we want to complete this picture, and if we want to continue this, grand story of propositions as types, we need to fill in what these bits are. So going back to the original problem, or the ambiguity problem over there, is that the issue here was that we weren't able to distinguish between these two different meanings in the same symbol, right? Because both of them are the same set of string of symbols, which is authority. So in semantics, you can do this. So there's a kind of semantics known as possible world semantics, sometimes called Kripke semantics, where what you will do is you won't just make a statement or just put a formula out there. You would say this formula is true in a given context. So the problem with this particular inference was that these two things were said in a different context, right? So we're going to capture that in our meaning. We're going to say, well, when we said the first proposition, Bob is an authority, that was in a context, whatever that context is, some W1, right? W for worlds. You can substitute worlds for context, freely, intuitively, that is. And then the second one saying I had authority was really said in a different context, right? So these in two different contexts. If they're in two different worlds or contexts, you can't actually infer in the same context that the I had Bob as a resulting inference, right? So this is known as possible world semantics, where all we're doing is we're now talking about meaning of things with respect to a context, right? And more formally, the way logicians do it is this is inspired from what the logicians did, but now we're doing it in a slightly more modern notation. So we're going to say, okay, here's a set of worlds, and then this is a way of giving semantics to your logic. So you've got a set of worlds, you've got an ordering relation on these worlds, and you've got a valuation function. Valuation function is basically just a way of saying somebody has to at some point tell you what is P true or false, right? That's a way of thinking about it, right? So now, similarly, now you say A and B is true at a world if A is true at a world and B is true at a world. A implies B is true if A implies B at all future worlds, right? So this is just a relaxation saying it doesn't have to be right away, just in this immediate context. It can also be in larger contexts. You don't have to do that explicitly for products because it can be shown, right? For conjunction, because it can be shown. So there's no harm in removing that. Right. But the interesting thing now is there is no proof system, remember? So, well, I've not discussed the proof system. Now we can reason about whether a formula holds or not. If the thing on the right-hand side is actually in a theorem prover. So if I actually write this as a function in Agda, where I actually take this syntactic symbol and give it a meaning, this being the product type in Agda, and these things being function type, Agda or any other dependently typed programming language or theorem prover, what we can actually do is we can talk about proving a formula just by writing programs, right? So we're going to write a program. So B and A is interpreted as a product of two things. And now what we're going to do is we're going to take this product and we are actually going to construct a new product and we're going to swap them, right? So now the correspondence is a little bit closer. So what we're doing to reason in the semantics, to reason about, to prove this formula, we're just going to write a program which does this for us, right? And of course, the reason we're doing all of this is because the dichotomy kind of broke down for modal stuff, and we're going to look at right. So now, for the good news is that we can actually do this for modal logic too, and that's the whole point of doing all of this, because that's where things broke down. So now, box A is understood, necessarily A is understood for all future worlds, meaning so future here I've introduced a new relation on worlds. In addition to less than equal to, which is just about context being lesser or smaller or greater, now you also have like worlds, and so you also have another relation between worlds, which is just an abstract relation. At this level, you don't care in the semantics, right? And box A is understood as roughly as A holds at all future worlds, R being the specification of future. And this basically means that possibly A means A holds in some world, right? So if A holds in some context, you can say A is possibly true. So that's the essence of what's happening here. How are we doing on time? I've got 5 minutes left. Okay, great. So excellent. So the news here is that so the inference here is that in this interpretation we can show that this thing here, this function space, is in fact a comonad, and this quantification here over the proofs is in fact a monad. Right. So now we can start saying some things. Now that we have meanings and we've got semantics and things, we can say things like box is a comonad in an appropriate sense when the relation is reflexive and transitive, and you can make things like, diamond is a monad when R is reflexive and transitive, and so on. Right. You can make a number of statements based on this interpretation, and this is how the connection to monads and comonads comes in, because we're no longer looking at the syntax, we're looking at what things mean. And you also find out quickly that maybe being an option in Java is a thing which is not a diamond, is not a possibility. So you're also getting some negative results when you start looking at the meaning of things, right? So actually, it's a bit of the ending actually says, so the box A is not a monad. In fact, box A is a comonad, but is not. You can't think of necessity as a comonad, right? So they're not equivalent concepts. What we've learned is that you can think of box A as a specific class of comonads, and you can think of diamond A as a specific class of monads. And the main kind of takeaway that at least for me is now we're going to study semantics, right? We're going to look at, since we don't have systems, we have to look at semantics. So that's what we're going to do, and we're going to study the semantics. The thing that I do is I study the semantics of these logics by interpreting them in a proof assistant, in a type theory. And this gives me a way to kind of interact with these logics and prove equivalences and so on. So in a nutshell, the summary is basically the meaning of propositions of meaning of types. And if you really want that slogan kind of thing, this is a bit of a work in progress, right? So what we're going to talk about, instead of proofs, we're looking at a kind of a entailment relation, which is a semantic notion of proofs. And this is about constructive entailment. And instead of equality of proofs, instead of reduction of proofs, we're going to talk about when these two entailments are equal, right? So when I say entailments, I just mean that little program we wrote in the meta theory in the type theory to reason about these formulas. Right. So now, is all this stuff useful, right? So this is a question I haven't quite answered. Why are we looking at modal propositions as types? So this brings me to what I actually do. So the reason that we're looking at this is modal logic has a really good advantage, which is that modal logicians study classes of modal logics, right? So they don't study a single modal logic, they study a number of things at the same time. This could really help PL research, because what we can do, we could benefit from studying classes of calculi, classes of languages simultaneously. So we're not spending time on one specific thing, then we can move a little bit faster, right? It's in a sense, all I'm talking about is reusability of properties and doing things for larger classes of things, which modal logic is good at, and we're trying to transport that to programming languages. Right, and this is the name of the project. The specific application that I'm interested in is in normalization. Okay, right. So I'm actually gonna stop there, and so it seems, so the thesis that I'm kind of working on right now is that we can leverage the modal logical semantics to look at classes of logic simultaneously to prove normalization, which is an application. Normalization is a very difficult thing to prove generally. Because you often talk about it for a specific language, and how can you do this for classes of language, right? And normalization is not just a theoretical property of interest; it's also an instance of optimization, which compilers do is an instance of normalization. So it would be nicer to stop doing this for a specific language and try to do this generally. So that's and all of this stuff is up online, and I try to do as much of this work publicly. Code is all open. Even the proposal of the project is up there. You can have a look just to get a sense for these things. And these are like high-level descriptions. The one I gave is a little bit more technical. This is actually just a layman's kind of, because it was supposed to be written for a larger audience. So this will give you a sense for what it is, the proposal. But if you really want to dig down what exactly is going on, get deeper, you can go to the really poorly documented code on GitHub. Okay, great. So what I'm going to do is actually end with a little shout out to TypeSig. So TypeSig, it's been really cool, I have to say. So I first heard about TypeSig through advent of proofs. And first I remember looking at hearing about advent of proofs and going, proofs for fun? Who does that? Like, it's so cool. Can you believe that? That's amazing, because that's like this organic collective embodiment of propositions as types, because what you're doing is you're writing proofs, but you're actually hacking and you're writing code. Like, I thought that was really cool. And I really kind of like also the community that they all have built at TypeSig, right? Because I looked at all the posts on the website, and every little post kind of ends with TypeSig art you. So it's one of the things which is quite difficult to do, at least in an academic setting, is community buildings, right? So I think it's really cool that TypeSig's done this really well. So big fan. Yeah. So I guess what I should end with is that, or maybe you want to call it that. It's really up to you. So thanks. We can do questions.
Hello? Yeah. Hello. Hi. Really great talk. I really loved hearing it. I had a question around the fact that you mentioned by doing what you're doing with modal logic, you mentioned that there's some properties from studying sort of PL as modal logic that you find could be helpful for the PL community. What kind of properties were you sort of thinking more particularly? What kind of things you think could be particularly beneficial for the PL community?
Right. So thanks for that question. That's the thing I kind of rushed over. So so this is the bit actually that. So one thing in modal, so in logic, what you do is when you have a proof system and if you have semantics for the proof system, what you want to do is you want to prove that there's a notion of completeness, right? You want to show that this proof system is complete with respect to semantics, which is just saying that it's the appropriate semantics roughly that for the proof system. So this is something that modal logicians have been doing for a long time, right? They've been proving completeness for not just one logic and one proof system, for a number of them simultaneously. In the other world of programming languages, we prove things for normalization, and it takes a lot of work to prove normalization for one calculus, right? We write a paper based on one normalization result. And I think somehow it's because we don't know how to abstract, or it's still work in progress as to how to abstract over this kind of, how do we do them collectively? So via this link of propositions as types, we could possibly, the hope is that we can borrow that kind of connecting syntax and semantics through the semantics in a way. We're gonna borrow their ability to study completeness for normalization. So the concrete properties that I have in mind, the thing that I'm interested in is normalization, simply because it's very difficult to do. It's very difficult to prove, and most of the time it's not proved because it's so difficult. And how can you make that easier is the thing that I'm particularly interested in. But hopefully it also applies to other things we care about in PL, like proving security properties and that kind of thing, but for a class of languages.
Thank you.
Thanks, and thank you for the talk. On the topic of normalization, and sort of as a follow-up even, I was wondering how well you thought projects like LLVM were doing towards having, I guess, a more programming language general optimization and normalization intermediary language, I guess.
Right. So, I mean, so I don't know a lot about the LLVM work in LLVM, but I do know that there are formal semantics and the optimizations are often justified. So the vision is that we can do that kind of thing. We want to be, so normalization is really, I talk about it like an abstract problem here because of time, but really it's about taking a program, normalizing it to something else, of which optimization is an instance. So in a sense, it should eventually cater to something as concrete as LLVM, but these things take time because you have to study them for models and then kind of expand them to something a little bit more real, like Haskell or something, and then actually go all the way, right? So it takes forever for these things to catch up. I understand. But the hope is it does, in some sense, at least be reusable. So what I would imagine is where you write, if there are optimizations for different parts in LLVM that you're doing, what I would hope is that you kind of have this common interface that you're using, and you write optimizations for interfaces, and LLVM is an instance of one, and maybe a different language is an instance of that. That's the kind of the grand vision.
Perfect, thanks.